In my last video, I introduced you to the four quantum numbers that define a unique electron: N, L, M sub L, and M sub S. And I also covered the rules for the allowable values for the quantum numbers. And it is those allowable values for the quantum numbers that tell us how and where the electrons are distributed in an atom. So these allowable values tell us how to fill electrons into the various shells, into the various energy levels. So as an example, if we have an N value equals 1, an L equals 0, and an M sub L equals 0, those are the lowest values that we can have for an N, L, and M sub L set. The lowest value for N is 1. If N is 1, there's only one possible L value, and that's 0. And if L is 0, there's only one possible M sub L value, and that's 0. And you may recall that I told you that the first three quantum numbers define the orbital, and the fourth quantum number, the M sub S, defines which electron of the two of them that can be in the orbital. So here we have a set of the first three quantum numbers that defines the lowest possible energy orbital, and therefore it is the first orbital that is going to get any electrons. So the fundamental principle here is electrons will fill the lowest energy orbitals first. And then now that we have defined the lowest energy orbital, the M sub S value can be one of two values because each orbital can hold 2 electrons. Well, I'm going to expand on this concept, and I'm going to represent it graphically so that you can see a diagram of how this happens. And because you've taken chemistry before, you have probably seen it before, and it is an electron diagram. And from electron diagrams, we can then write electron configurations. So let's move on to the next page. The first thing we're going to do is we're going to draw an electron diagram with empty orbitals. So electron diagrams make it easier for us to visualize the filling pattern of the distribution of electrons and how they fill up the energy levels. So we're going to sketch an empty, with no electrons in it, an empty electron diagram all the way up to and including the 5s orbital. So as I do this, I'm going to take care to write over on the left-hand side of this page, and I'm going to save some space over on the right-hand side of the page to duplicate my work later, and you'll see why. So here we go, and I want you to take special note of the numbers and the letters that I use. So we start out with 1s, and then we go with 2s, and then it's 2p, and then 3s, and then 3p, and then 4s, and watch this number is 3d, and then 4p, and then way up here at the top is 5s. So these are the n values, the numbers are the n values, 1, 2, 3, and so forth. And the letters, you will recall, represent L values. S means the L value is 0. P means the L value is 1. And D means the L value is 2. So now that I've done that in that sequence, I'm going to draw a flat line, a little dash there, a space, for each orbital. Now in an S subshell, we know that there is only one orbital in that subshell. I'll remind you of this diagram. If we have an S orbital, there's only one orbital in that subshell. If we have a p orbital, we have 3 of them. If we have d orbitals, we have 5 of them. And if we have f orbitals, then we have 7. So that's the way we're going to use this here. So everywhere we have s orbitals, or s subshells, we're only going to have a single orbital. Like so. Everywhere we have a p subshell, we have 3 of them. 1, 2, and 3 empty orbitals. 1, 2, and 3. P subshell, 1, 2, and 3. And everywhere we have a d subshell, we have 5 orbitals. And if I had an F subshell on here, then I would have 7. But I don't have any yet because we've only gone up to the 5s, and there are no F orbitals yet in that sequence. So let me explain what we're looking at. We are looking at empty orbitals, and this orbital, this flat line, represents an empty orbital. I could have drawn it as a circle or as a box, but I chose to just draw it as a straight flat line, and that signifies an orbital with no electrons in it. And then we have the subshells over here, the 1s subshell, the 2s subshell, the 2p subshell, and so forth. And this is the sequence that electrons are going to fill into orbitals, because these are the orbitals from lower energy to higher energy. So I have just shared with you one of the 3 key rules for filling electrons in an electron diagram. Electrons fill the lowest energy orbital first, and then they build up from there. And this, in parentheses, this is called the Aufbau principle. Aufbau is a German word. It means to build up. So we are building up. We're aufbauen, upbuilding. So electrons go from the bottom up, from the lower energy up to the higher energy. So that's the first rule that tells us how to fill in electrons in that diagram. The second rule is that electrons must have opposite spin if they are paired up, which is to say, if you have 2 electrons in the same orbital, they must have opposite spin. You remember how I mentioned that we have an up spin and a down spin? So if they're paired up in an orbital, they must have opposite spins. And this is called the Pauli exclusion principle. And then the third rule that tells us how we're going to fill in electrons into this electron diagram is that 1 electron has to go in each orbital of the same energy level. So if we have 3 orbitals that are along the same energy level, that is called, if they are of the same energy level, they are called degenerate. And in this sense, the word degenerate is a specialized technical term, and it just means orbitals with the same energy level. So in a p subshell, we have 3 degenerate orbitals. In a d subshell, we have 5 degenerate orbitals. So the rule here is that before we start to pair electrons up in an orbital, we have to put 1 electron in each orbital in that subshell of that energy. So another way to say it is we're going to put an electron there and then an electron there instead of putting 2 electrons here. Okay? And this rule is called Hund's rule. HUND'(S) rule. And there we go. These are the 3 rules that are going to direct how we fill electrons into this electron diagram. The Aufbau principle, the Pauli exclusion principle, and Hund's rule. So we're going to follow these rules here in just a minute when we start to plug in electrons into our electron diagram. Before we do this, I want to take a moment to direct your attention to your periodic table. So if we look at our periodic table, the periodic table is organized based on how electrons fill orbitals. So again, the periodic table is arranged based on this electron filling pattern. So I'll take a moment here and I'll point out these first 2 columns, these first 2 groups. This is called the S block of elements, right there. Those 2 columns called the S block of elements. And that is because that they represent the 2 electrons that go into the s orbitals. And I'll show you how that happens in just a moment. As we look over here on the right-hand side of the periodic table, these last 6 groups, 1, 2, 3, 4, 5, 6, so it's groups 13 through 18, these are called the p block. Related to p orbitals, and it's the block of elements. It's the p block of elements, okay? And you'll notice there are 6 columns, and they correspond to the 6 electrons that would fill into a p subshell. Moving on down to the transition metals, you may have noticed that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 groups, 10 columns, and those correspond to the D block. They are the D block of elements because those 10 columns correspond to the 10 electrons that fill in the D subshells. And then that brings us down to the bottom 2 rows down here, the lanthanides and the actinides, what we also call the inner transition metals. And these are the F block of elements. The F block of elements, and you might notice that there are 14 columns here, and the 14 columns correlate to the 14 electrons that would fill in the 7 orbitals in an F subshell. So the periodic table is actually arranged according to this filling pattern. Well, let me show you how these numbers enter into it as well. If we look at the number of the row that the elements are in, these numbers correspond to n values, right? So I could say this is n equals 1, n equals 2, n equals 3, n equals 4, and so forth. And there's an important exception to that for D block and for F block, but generally we're going to use these. So let's take a look. Let's start with hydrogen. Hydrogen has 1 proton in its nucleus, and it has 1 electron orbiting the nucleus. So where is that 1 electron going to go? Well, if I look at my diagram and I follow the Aufbau principle, that 1 electron is going to go right down here, isn't it? So I'm going to use a different color here, and I'm going to put my 1 electron for hydrogen right there. And there's my 1 hydrogen electron. And notice that it's located in the 1s subshell. 1 electron for hydrogen in the 1s subshell. And if we look at our periodic table, there's the n equals 1, and it's in the s block, and we know it has 1 electron. So the 1s subshell. So this then leads us to being able to write out what we just said. We want to say that hydrogen has 1 electron in its 1s subshell. And so there is a way for us to write that without having to draw the diagram every time. And it's called an electron configuration. So the way that we write electron configurations is we start by writing the symbol of the element that we're talking about, and then we follow it with a colon because we're about to say what the electron configuration of hydrogen is. Then we write the subshell, and in this case for hydrogen it's 1s. And then we write how many electrons are in that subshell. So there's 1 electron. So we write it, the number of electrons, as a superscript. And there's the electron configuration for hydrogen. So hydrogen in the 1s subshell is 1 electron. Let's move on and deal with helium as the next one. So helium So helium is way over here in the very last column on the periodic table. And it's written there generally because it is a noble gas, and so its chemistry is like the other noble gases. But there's also a good argument for writing helium right here. And we can pretend for a moment that helium fits right there. And the reason that helium fits right there is because it has 2 electrons. Its first electron fits in the 1s subshell, and its second electron also fits in the 1s subshell to give us a pair of electrons in that s orbital. So we're going to put our second electron here, and now we have helium. And there's helium. Helium has 2 total electrons, and this is where they go. The Aufbau principle says that that second electron cannot jump there or there or there to begin with. It has to start out here in the lowest possible orbital, if there's space. Then the Pauli exclusion principle says that if it's pairing up with another electron in that orbital, it has to be spin flipped. It has to be the opposite spin. So now what is the electron configuration for helium? Well, in the 1s subshell, it has 1, 2 electrons. So for helium, the electron configuration of helium is, in the 1s subshell, it has 2 electrons. Now I believe this is a review for most of you. You should have had this in your previous chemistry course. If you took Chem 130 or high school chemistry, you've seen this before. So I'm hoping this is a review. So we're going to move on now to adding more electrons. And as we do, I would like for you to take note of the periodic table. So what we're going to do is we're basically going to start counting off the number of electrons that an atom has. So let's take, for example, let's see. The next one is going to be lithium. It has 3 electrons. And without even looking at the diagram, I can tell you where those electrons are going to go. I'm going to have a 1s1, 1s2, so I'm going to have a 1s2, and then I'm going to have a 2s subshell, and I'm going to have 1 electron in it. So the electron configuration for lithium is going to be 1s2 and 2s1. So let's confirm that by taking a look at the electron diagram. Lithium, Li, has 3 electrons. The first 2 go here, and the third one goes here. So there's lithium, and therefore it has a 1s2 and 2s1. So on the next page, there we go. And just to review, it means in the 1s subshell, we have 2 electrons. And in the 2s subshell, we have 1 electron. Let's expand it to oxygen. So now we have oxygen here. Oxygen has 8 protons, and therefore a neutral oxygen also has 8 electrons. Where are those electrons going to go? Well, we can count them out. In the 1s, it'll have 1, 2. So 1s2. In the 2s, it'll have 1, 2. So 2s2. So 1s2, 2s2, and 2p block, 2p, 1, 2, 3, 4. So 2p4. So oxygen's electron configuration, without even looking at the diagram, I can tell that it's going to be 1s2, 2s2, and 2p, 1, 2, 3, 4, 2p4. Okay? Let's see what that looks like on the diagram. Let's fill in those electrons. 8 electrons for oxygen, right? So there are the first 3. There's 4. There's 5. And now we have to use Hund's rule that says every degenerate orbital gets 1 electron before we pair them. So I don't pair it right here first. I have to put my number 6 right there, my number 7 right there, And now I can pair them up, and I'll give it its 8th electron. 1, 2, 3, 4, 5, 6, 7, 8. So that's the electron configuration of oxygen, 1s2, 2s2, 2p4. And again, looking at the periodic table, we could count that out without having to have a diagram of it. 1s2, 2s2, 2p4 for oxygen. Okay? So our next one that we're going to do, let's go ahead and write that down. Oxygen, just so we have it here. 1s2, 2s2, 2p4. All right, so now we're going to work with bromine. So let's find bromine. Bromine is here. It has 35 electrons, 35 protons, so it must have 35 electrons if it's neutral. So I'm going to fill in the diagram with 35 electrons. So here we go. We've already got 8 there from the oxygen. So here's 9, 10, 11, 12, 13, 14, 15, 31, 32, 33, 34, and 35. So there is the electron diagram for bromine. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Well, is there a way to determine all of that without having to draw a diagram and fill in the electrons? Sure. Let's take a look at our periodic table. Bromine is down here with all of these electrons, so we're just going to build it up the way we were earlier. So bromine has 1s2, 2s2, 2p6, all 6 of these are filled for bromine. And we get to 3s2, go across, 3p6, down to 4s2, and then we hit the D block. And there's a special rule here for the D block. So the rule for the D block elements is that their n value is 1 less than the row that they're in. So I'm going to make a little note here. D block elements, the n equals 1 less than the row. So after 4s2, I would get to the 3d subshell, and it would be 3d10. And then back up to the n equals 4, because we're now in the p block, so it uses the same row number that it's in. So this is the 4s, the 3d, and back up to the 4p. So we got 4p, 1, 2, 3, 4, 5. So again, bromine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. And we were able to do that just by looking at the periodic table. We didn't need that chart. Notice here how the 4s and then the 3d and the 4p, that's what happens, the 4s and the 3d and then the 4p, okay? So let's fill in the electron configuration for bromine. One s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Okay. All right, that brings us down to example F. Now we're going to do tantalum. So tantalum is right here. So I want to remind you that D block electrons have an n value that is 1 less than their row. So this is the 6s, and this would be the 5d, right? However, there's something else going on here. Look at this 57 for lanthanum, right next to 72 for hafnium. Why do we have a gap there? The reason there's a gap there is because this row right here fits right there. These are the inner transition metals, and they actually belong right here. The reason they're written down here is because if we put them in there, then the periodic table would be too wide to fit on a page. So they're just pulled out and written down here. But that Ce, cerium, goes right after the lanthanum. It goes right there. The other quirky part of this is that the F block takes an N value that is 2 less than the row that it's in. So if this is 6s and this is 5d, then this is 4f. 6s, 5d, 4f, okay? And we have to account for these electrons. So there are 14 electrons here in the 4f subshell. All the way over, 4f subshell. And they should be included in your electron configuration for tantalum. So here we go. We're going to count it out just by looking at the periodic table. The electron configuration for tantalum. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and we're going to have 1, 2, 3 electrons in the 5d subshell and 14 electrons in the 4f subshell. So here we go. We're going to write all that out. Goodness, here we go. Tantalum, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. So far, that 4p6 takes us through krypton right there. So far, so good. Now it's 5s2, 4d10, 5p6. So that 5p6 now takes us through xenon. And after xenon, we have 6s2, and then we have 3 electrons in the 5d, and then 14 in the 4f. So 6s2, 3, oops, I'm sorry, this is in the 5d, we have 3 electrons. And then in the 4f, we have 14 electrons. So there is the electron configuration for tantalum. Now you can tell that this gets to be quite tedious. So there is another way to write this in a simpler way, and you may well remember this. You may have been wondering why we didn't do it already, but I just wanted to show you what it's like without taking the shorthand method. The shorthand method is also called the noble gas shorthand method for writing the configurations. So to save time and space writing the electron configurations, we can write a chemical symbol for a noble gas in brackets to represent the core electrons of a species. And then we just add on any other electrons in the valence or outer electron shell. So remember when I said that for tantalum, once we got to the 5p6, it was the same as xenon? So I could write tantalum just by writing xenon in brackets, and that represents all of the electrons leading up to there, and then just adding on the additional electrons. So We're going to do that sort of thing with silicon. So I will do this for silicon, and then I will ask for you to do it for barium. So for silicon, and you notice I'm not even looking at the diagram anymore. I'm just looking at the periodic table. So here's silicon. So I could write out all of the electron configuration. I could write out 1s2, 2s2, 2p6, 3s2, 3p2, 1, 2. Or I could let a noble gas represent the core electrons. So the way that we do this is we look at our element that we're going to be writing the electron configuration for, and we find the noble gas that came just before we got to that element. We don't look forward for the next noble gas. We look backward at the last noble gas in the sequence. And in this case, it's neon. So we're going to let neon represent all of the electrons leading up to neon. And so the electron configuration for silicon. So neon in brackets, that's the noble gas shorthand that represents all of the electrons leading up to neon. And then beyond that, beyond neon, we have 3s2, 3p2. And so it allows us to write the electron configuration with a little bit of a shorthand notation. So how would we write tantalum up here? Well, again, I could let xenon represent all of these electrons right here. And then I would just add on the remainder. So it would be 6s2, 5d3, and 4f14. So you can see that using the noble gas shorthand would save us a lot of writing in the case of tantalum. So with that in mind, I would like for you to do this last problem here. Example B, write the shorthand electron configuration of barium. And when the question specifies to use the shorthand notation, you do have to use that shorthand notation. So remember, it's the noble gas that goes in the brackets, not the element that we're giving the electron configuration of. So this is for barium. So I would like for you to do that. Complete that one with the noble gas shorthand electron configuration. Pause the video for a moment, and when you're done, resume the video and I'll work it out. Okay, coming back to this problem, we're going to write the electron configuration for barium. And yes, I could count it all out, 1s2, 2s2, 2p6, 3s2, 3p6, and so forth. Or I could just use the noble gas shorthand. So I look at barium, and I look at the noble gas that came before it. Not the one that comes after, but the one that comes before. So if I go back 2 spots, I find xenon at atomic number 54. So I'm going to let xenon represent all of the electrons leading up to xenon. And then I only have to add 6s2 right there. So it's basically going to be xenon 6s2. Noble gas goes in the brackets, 6s2. And there's the electron configuration of barium. And you notice how I was able to do that without even looking at the diagram. I did not have to draw a diagram and fill in electrons, right? I could do it just by looking at the periodic table. All right, so that is how we determine electron configurations, how we use the noble gas to write the shorthand configuration, and how we can use the 3 rules, the Aufbau principle, the Pauli exclusion principle, and Hund's rule to fill electrons in an electron diagram. So just a quick comment here. This electron diagram is just a visual representation of the quantum numbers. So this is a visual depiction of the quantum numbers. And then when we get to electron configuration, this tells us where all of the electrons are for a given atom. And in our next video, I'll be talking about some exceptions